bond polarity it deals with when we're talking about bonds, particularly covalent bonds. So a covalent bond is when electrons are being shared between two atoms so that they can act as if they're reaching their octet. So you guys remember what octet is? We talked about it last time before you guys left. Well, I'll give you guys a reminder what the octet is, okay? So in other words, we're trying to find a way that a atom in a chemical compound can act as if it has its energy shell full, just like the noble gases. So it acts just like the noble gases is the ultimate goal, right? And so the way that you can do that, there's only 3 ways that you can do it. You can either take electrons, you can give electrons, or you can share electrons. Covalent bonding is sharing of electrons. There's 2 types of sharing of electrons. One is even sharing and one is odd sharing. How many of you guys have siblings? Okay, so I have 2 sisters. I'm the oldest of 3, and I come from a pretty poor family. You know, growing up, we would get one really good gift, and then we would get like underwears and socks for Christmas, our gift. So one year we got an Atari, and so I'm kind of dating myself, I know. So that year that we got an Atari, my mom said, once we got it and everything like that, you guys got to share it and everything like that. Well, you know, I was going by my mom's rule, you know, we share it and all. So we get out of school and everything, and I pick up my sisters. We get to the house, and I have to watch my sisters. My dad was out on the boat, he was in the military, and my mom was working 2 jobs at the time. And so I'd watch my sister until my mom got home. And so basically, it would be about 4 hours before she had gotten home. So during that 4 hours, I would basically play with the Atari for about 3.5 hours. And then 30 minutes before my mom was getting ready to come through the door, I let my sister 30 minutes. And then I'd go in the kitchen and start, you know, cooking something, because she'd always come home hungry. So then after I finished cooking and everything, and she saw me cooking, because I'd finished like probably 30 minutes after she gets in the house. And then I said, okay, so it's my turn to play the Atari, right? So I gave my sisters about an hour to play the Atari. I played with it for about 3.5 hours, and then I played with it for about another 3 hours after, right? Before my mom said, you got to do your homework and go to bed, right? So, so I'd say I probably have the Atari about 90% of the time. My sisters would have it about 10% of the time. So is that sharing? Is anybody going to answer me? Everybody's on mute.
Yes.
No.
No, it isn't
Sharing.
That's hogging. That's hogging it.
But it's sharing. Did they get to play with it?
Yes,
It is sharing technically.
sharing. It's not equal, but you're sharing it.
Okay,
Yeah.
so that's my point. Okay, so we have 2 types of sharing. We have what we call polar covalent bonding, and we have nonpolar covalent bonding. Okay, so polar covalent bonding is when we share unevenly. So the electrons are being shared unevenly.
So you did polar covalent bonding.
That's correct. Yeah, I was an expert at it. I learned it to the T, you know. And then non-polar covalent bonding is evenly shared. Okay, so this here represents a bond. That line represents 2 electrons being shared between carbon and the hydrogen. Okay, so in this context, because their electronegativity. Electronegativity is the kind of like the desire to get an electron or the pull of the electron. So whoever wants it more gets to pull the electron a little bit closer to them, okay? These guys, carbon and hydrogen, are about the same in terms of their electronegativity. They're a little bit off. I'm going to give you some values. So if our X value is 0.4, is less than 0.4, less than or equal to 0.4, it's considered to be nonpolar. If our X value is greater than 0.4, but less than 1.8, it's considered to be polar. And then if our X value is, if X is greater than, 1.8, greater or equal to, then it's considered to be ionic or have ionic character. Okay? Are you with me so far? Okay, so we take the difference between the electronegativity. So remember, we're looking at carbon and hydrogen. So we're going to go to P table. I'll switch my sharing to the screen and open up P table. Oop, right there. Oh, I just crashed. Okay. Are you guys with me? Did I lose you?
No, we're here.
Okay. Okay, so if you go to your periodic table and you click on electronegativity, it'll bring up this scale here. There's also a table in my lecture notes. You can actually use that as well too. But here, if you take a look at carbon and hydrogen. So this is the electronegativity associated with it. So carbon has a 2.55. And so we're going to subtract hydrogen because it has a lower value. And we look at the difference. What is the difference? 2.55 minus 2.220?
0.35.
Okay. So where does that fall into our scale? Let's go to our scale.
Well, it falls into the nonpolar.
It falls into the nonpolar. That's right. So it would be considered a nonpolar bond. Okay. So if we're looking at oxygen and carbon, so oxygen is right here, carbon is right here. So we take the larger value, oxygen, we subtract carbon. What do we get?
0.89.
Okay. So if we go back to our little table there, we had a 0.89 value. So is that polar, non-polar, ionic?
Polar?
Polar, right? Because 0.89 is between 0.4 and 1.8, right? Okay, so then that's how you would rate it in terms of polarity, right? bond polarity. Okay, so bond polarity is just looking at a single bond between two atoms. Molecular polarity is looking at the whole atom. And we'll talk about that here in a minute, okay?
Do we always subtract the greater?
That is correct, because you're never
Okay.
going to have a negative value, right? So you're always going to take, it's going to either be 0 or it's going to be greater than that. You're always going to take the larger value. And then that basically means that the electrons are spending more time, in this case, electrons are spending more time around the oxygen than they are spending around the carbon. Okay,
Thank you.
so remember that uneven sharing, right? So which one would I be? Would I be oxygen or would I be carbon?
Oxygen.
I'd be oxygen because I'm the stronger one and I have to elect the Atari majority of the time. Right? Okay. So the stronger one is going to be pulling the electron towards it most of the time, and the weaker one is going to get it less of the time. That's why we always surprise that difference. Does it make sense?
Yeah.
Okay, good. Can you hold on 1 second? We're good.
Dr. Henry, I have a question.
Yep.
Will these type of questions be on the exam?
Yes.
And then, so will we have access to your P table during the exam, or how do we find
You will
their?
you will have access to P table.
Okay.
Yeah, or you would have access to those numbers. On those
Okay.
questions.
Thank you.
So if I remember correctly, Daisy, didn't you have access to numbers?
Yeah, you provided the action numbers.
Okay. Yeah, see, I'm not completely crazy. Maybe a little crazy. Okay. How are you guys feeling so far? Not too hard?
Not too hard.
Okay, excellent. So let's see if we can make it hard. Okay, so this is dealing with sharing, right? And so what we're going to do, we're actually going to go back to ionic bonds because that's where I wanted to start. But Daisy kind of pushed me in the middle. So you will see this again here a little bit later.
Trying to get it right this time. Come on.
No, I get it. I get it. I like you. See, she's being proactive, right? She's pushing me. She's driving the conversation. That's what you want to do. So we've talked about ions before too, right? Remember cation, meow, cation? No?
Yes.
Okay. So, boy, I know you guys are on break. You're like, he's expecting us to remember chemistry. That was all last, a week ago. Okay, don't worry. We'll get it. We'll get it. Okay, so let me get the normal table up here. There we go. Okay, so we did talk about everybody wanting to be like a noble gas, right?
Yeah.
Yeah.
Okay, good. Okay, but before we get to this, before we get into ions, we're going to talk about one other thing. I want to remember how much you guys do remember. I'm going to see if I can get some of those cobwebs off. You guys thinking again. Okay, so we talked about, let's see, what atomic radius? Or if we think about it, the size of the atom, right? So the atomic radius. So now if we know the trends of the periodic table, right, what you guys are doing, I know you guys know it. So is it going to increase from left to right or from right to left? So in other words, is the atom going to get bigger from the left to the right or from the right to the left?
The
left to the right.
It gets
Right
bigger?
to the left.
Okay, so Daisy says this way, and everybody else is saying the other way.
No, I meant, so it starts from the left would be the smallest, no, small, and then to the right it goes smallest.
Ah,
Down it
So-
goes.
And then it's
so,
gonna
Energy increases.
so from
left
right to left, that's what you're saying then.
right to left, and then it's gonna decrease as you go down.
Yes.
Okay, so that is correct. So it's going to increase as we go from the right to the left. So that means that it gets bigger this way, right? So these guys are bigger than, let's say lithium is bigger than oxygen. Okay, make sense? Okay, and then Daisy, you also said, was it from top to bottom or bottom to top?
It was from the top to the bottom.
Bottom.
From top to the bottom, it also increased.
I read it right this time.
That's
Last week
right.
I got it wrong.
Okay, so atomic radius is going to increase from right to left and from top to bottom. And we kind of think about it, top and bottom makes sense because it's kind of like, remember I told you, it's like the Russian dolls. I need to buy some Russian dolls. You guys know the little Russian dolls? The
Yeah.
little doll in the middle, next doll, the next doll, the next doll, and it just keeps getting bigger and bigger and bigger. So it's like a shell on top of a shell on top of a shell on top of a shell, right?
Mhm.
And so that's what happens as we go down. So that one makes sense. Not too hard, not too much to think about. Now, the fact that it's increasing going this way, right? Even though in theory you're getting more electrons added going the other way, that makes us think a little bit. And the reason why that happens is because these guys are all in the same energy level. So basically, they have a limit that they can get to, right? So what happens is that because the center is positive, the more positive that you have in the middle, the more it's pulling those electrons closer to it. So the more positive charge you have in the middle, the more you're going to pull everything a little bit closer. Does that make sense?
Yes, it is.
Yep.
Okay. So that's the reason why it actually gets smaller as it goes from left to right, or it increases as we go from right to left. Okay. Piece of cake so far?
I understand it, but I'm not gonna remember it.
I like somebody who's, I understand it, but you know, you the more you look over it, you'll remember it. But fortunately, it's like 1 or 2 questions on the test, but it's all going to be important later on, though. Then things will be like, oh, that's why that happens. Okay, so let's talk about ionization energy. Okay, so ionization energy. So which way is that going to increase?
Left to right.
That's right.
So you said left to right. Okay, you guys remember what ionization energy is?
No.
Okay, well, we'll talk about that here. At least you're honest. No. Okay, what about, okay, so ionization energy is the energy that it takes to remove an electron. Okay, so nothing is for free, right? You know, I know you guys see the commercial with TurboTax, free, right? And how many of you guys actually use TurboTax? Is this for free? Any of you guys?
No.
No? Okay, so we're talking about ionization energy. So ionization energy, as I was saying, nothing comes for free. So it takes a little bit of energy to remove an electron. There are going to be certain elements that are cool with electrons being removed, so they're not going to take that much energy. And there's going to be other ones that are going to take a lot of energy, okay? So it's the energy to remove an electron. So you guys were right. It increases from left to right. So the one that it takes the most energy to remove an electron is going to be who? Who do you guys think it's going to be?
Hydrogen.
Now remember, it increases from left to right.
Helium?
Oh, helium.
Helium, okay? So the reason why it takes so much energy to remove an electron from helium is because first off, it's a noble gas. It's happy with the number of electrons it has. It's like, you know, I'm rich. You don't mess with me, right? And then you try to steal from me, I'm coming after you, right? So it's like, I'm really strong. I am not giving it up. It's going to take a lot of energy to sit there and remove that electron. Okay, so who's going to be the weakest? Who's going to take the least amount of energy?
Hydrogen.
Hydrogen.
It's going to be
Right.
hydrogen. Who's it?
Or francium.
Francium.
Francium?
Yes. So francium is way down here. Its ionization energy is really, really weak. It's kind of like almost to zero. I mean, it's not really, it's pretty low. It's not zero, it's about 100 something, but it's really low compared to what you're going to get into the thousands in the case of helium. Okay, so ionization energy is just like that energy to remove an electron. The second ionization energy is to remove 2 electrons. The third ionization energy is to remove the third electron after you remove the first 2. And each time it's going to get harder and harder. Okay, so that's something that you want to keep in mind. Okay, except for the ones that want to get rid of electrons, you know, 2 electrons. They're like, hey, it gets a little bit easier for us, you know. Does that make sense?
Yeah.
Okay. And then electron affinity. If you have an affinity for something. Affinity. Do you know what that means? That term? Anybody want to take a guess?
Abundance?
Not abundant. That would be in, like infinity would mean like forever and ever and ever, right?
Oh,
Affinity means kind of like, like I have an affinity for ice cream.
You really like it?
I really, really want it, right? I really want ice cream, even when I shouldn't be having it. I love ice cream, right? So, well, and strawberry cake. So together, I have a huge affinity for ice cream and strawberry cake. Okay, so electron affinity is the desire to get an electron, add an electron. So who's going to have the biggest desire to add an electron?
hydrogen?
Who's that?
Hydrogen?
Hydrogen? Well, hydrogen is going to have a little bit of one, but think about some of the guys that we kind of talked about. I said he's a bully, he's
An atom.
Oh, the noble gases.
no gas. Do they want to get an electron?
The
No.
nonmetal?
So it's going to be non-metal. So the non-metals, all the non-metals are going to have a higher affinity to gain an electron. That's true. So that's true. But which non-metal do you think is going to be the biggest one? You know, it's going to be, oh God, I am just this close away from, and it isn't hydrogen. Although I can understand why you would think that, but it isn't hydrogen.
Would it be iodine?
No, iodine would be, he belongs in that family, but he's not the one that is the most.
Chlorine?
Fluorine.
Chlorine.
Yes. Chlorine is like the biggest bully, and you're going to hear about him a lot. He is just like, I am this close. I am this far away from being a noble gas, right? And a cool noble gas on top of that, right? So I'm going to do everything in my power to get that electron. So he's going to have the highest electron affinity. He's going to want it more than anyone else, okay? So electron affinity is going to increase which way?
Left to right?
Left to right. So now if we say that fluorine has the highest electron affinity, so who's going to have the lowest electron affinity?
Hydrogen.
Would it be hydrogen? I think where fluorine is at.
Francium?
Francium. Yes, francium is also going to have, because francium doesn't want electrons. Really, he's like, I'm trying to get rid of electrons. Oh, why the hell would I take some, right? He's like, no, that's not my thing, right? So it increases from left to right, and it increases from bottom to top. Okay? So far? Are you guys remembering any of this?
Yeah. And I'm writing it down on your chart. It looks all.
Okay, so we have one more, then we can move on to chapter 12.
Increase. And up. Increases up.
metallic character. Okay, so metallic character is going to increase in what way? Left to right or right to left?
Right to left.
Okay, from top to bottom or bottom to top?
Gonna increase from top to bottom.
That is correct. Okay, so metallic character is going to increase from right to left. That makes sense because all the noble gases are pretty much over here. And as we move here, we become more and more of the metal, right? Because we go from noble gases, we go to non-metals, and then we go to metalloids, and then we become metal. Okay, so that makes sense, right? If you look at the periodic table. Yes, no, maybe?
Maybe.
Yes.
Okay. Okay, so let's see how much you guys remember on Lewis dot structures. So sodium. Sodium has how many, well, what is the electron configuration?
One S2.
Oh, you're gonna do it the hard way, huh? You're not gonna use the shortcut?
Oh, just kidding. No.
Okay. She is like, we're gonna start from scratch. So give me the shortcut, if you can.
Is it on line 3? 11.
Na, we're looking for
Na?
Na, sodium, yep,
Neon in a bracket.
Yeah.
okay.
And then 3s1.
Okay. Okay, so we know sodium. Sodium is right here. Now, if it wants to be like a noble gas, what is the nearest noble gas it's going to want to be like?
Yeah.
Yeah.
So what does it need to do to be like neon?
Needs to lose one.
It needs to lose one electron. So when it loses an electron, it becomes positive, right? It has a positive charge associated with it because the number of protons outnumber the number of electrons. So we lose one electron. So we just end up with Ne. So then this guy would have the same number of electrons as neon. The fact that it has the same number of electrons as neon makes it isoelectronic. Okay, so it gives it that plus charge, right? Meaning that it's lost out of one electron and then it has just the same number of electrons as neon. Does that make sense?
Mm-hmm.
Okay, so if we draw the Lewis dot structure for sodium, just sodium, not sodium ion, it would just be Na with a dot because it has one valence electron. The way that we calculate the number of valence electrons, we're going to be talking primarily with these guys and these guys. This here's the S, you guys remember, and this is the P. Right? And all you would do is count the number of electrons that would be, in this case, in that third one till you get to sodium. So that would be one valence electron. So it would have one dot. Okay. So if I was talking about oxygen, okay, how many valence electrons does oxygen have?
6.
1, 2, 3, 4, 5, 6. So we would make it have 6 dots. Okay.
Mhm.
So for oxygen to be like neon, then how many dots will it need?
2 more.
Would have to lose 2, right?
Would it lose 2 or would it gain?
It would take 2.
Take
It would take 2 more. So we need to get 2 more. So if it has 2 more, then it becomes O2. Right? Meaning that there's 2 more electrons than 2 additional more electrons than the number of protons. Because
It's a
we know
negative?
that- what was that? It makes it
It's
a
a-
negative charge. That's right.
Okay.
Okay, so this guy, the sodium, the Na plus, that would be a cation. Because cations are positive. Remember? Positive. I know I said that, Joe.
Now I remember.
Okay. And oxygen here would be an anion because it's negative. Okay. So you see, come on. Okay, so cation, positive charged, anion, negative charge. Okay. So now we've talked about those ions, right? So positive charge, negative charge. So these are examples of other ions that are isoelectronic to neon. So we know that nitrogen, if nitrogen gains 3 electrons, it'll have the same electron configuration. Oxygen, we just talked about, if it gains 2 more electrons, it'll have the same number of electrons as neon. See, O2 minus, nitrogen, N3 minus. Chlorine, if it gains 1 electron, it will have the same electron configuration as neon, F minus, okay? And then, of course, we know what neon is, okay? We had just talked about sodium. So here's sodium alone. Sodium loses 1 electron. It becomes the same thing, same number of electrons as neon. Magnesium, if it loses 2 electrons, it has 2 valence electrons, it becomes the same electrons as neon, okay? Aluminum, if it loses 3 electrons, it becomes the same thing as neon, okay? So again, these guys are going to become what we call isoelectronic, meaning the same number of electrons as neon, okay? This table just basically shows you things that are isoelectronic with each other. These guys that are in green, these are all isoelectronic to helium. So our hydrogen ion, our lithium ion, okay? Do you guys get that? Okay. Yeah, no, maybe? Okay, so now that brings us back to that point, to be like the noble gases, right? So when I say they want to be like the noble gases, it means that they want to have the same number of electrons as the noble gases because they are stable with the number of electrons that they have, okay? So things are trying to find ways of doing that. There's a couple of ways of doing that. Like we said, you could give or you can take. So if you're giving up an electron, you become positive. If you take an electron, you become negative. If you give up 2 electrons, you become 2 positive. Okay, if you give up 3 electrons, you become 3 positive. Okay, so we have carbon here. Carbon is kind of a special case, right? Carbon can go, in a sense, it can go either way. It can give up 4 electrons or it can take 4 electrons, right? To be like a noble gas. Makes sense, right? You count.
Mhm.
1, say 1, 2, 3, 4. And then it's like helium, or you can gain 1, 2, 3, 4. And it's like neon. So that one's always, it can go either way. So it really just depends on who carbon is with. Okay. Nitrogen. Nitrogen, it has the option. It can gain 3 electrons, 1, 2, 3. But if it loses 5 electrons, 1, 2, 3, wait a second. 1, 2, 3, 4, 5, it can be like helium. Now, which one is it going to want to do?
Take.
It wants to take, right? Why does it want to take?
No
Because
one-
it's greedy.
Because
The
it's greedy?
electronegativity, right?
Well, yeah, it does have electronegativity. So that's true. So that's actually a very valid point. But one of the main reasons, because it's less energy. At the end of the day, it's all about energy. So if you have a choice to walk 3 blocks to a store or walk 5 blocks to a store, which one are you going to do?
3.
3.
Right? Especially after a long day of work, you ain't going to want to walk 5 blocks, right? So you're going to go to the one that's closest. That's exactly what they're going to do, right? So the elements are looking for the easiest way, the lowest amount of energy. You know, they're just like us in a lot of ways. They just want to keep it low energy, right? Does that make sense?
Yeah.
Okay.
Yeah.
Okay, so they're always going to look for the easiest way of getting there. Okay, so let's see. We have phosphorus. Let's see. Aluminum.
It's going to try to be like neon.
It's going to be like neon. So it's going to lose how many?
3.
Okay, so aluminum is going to lose 3 electrons. So then it's going to have an Al3+. Okay. So nitrogen, you said was going to gain 3 electrons.
So it'd be 3 negative.
So it's going to be 3 negative. So now this does not happen in a bubble. So usually it's about give and take, right? They kind of go together. So somebody is usually giving and somebody is usually taking, okay? So if we put aluminum and nitrogen together, what happens is that aluminum is like, okay, I have enough energy because nitrogen's kind of got me motivated, got me worked up, that it wants to give up those electrons. And nitrogen says, yeah, I'll take them, give them here, right? And so they do an exchange. Aluminum gives nitrogen its electron. So then aluminum becomes 3+ and nitrogen becomes 3-. But they also form what we call an ionic bond. So an ionic bond allows these guys to cancel each other out, balance each other, to make each other stable charge-wise too, because it's best to try to have a neutral charge if you can get a neutral charge, right? Or find a way of getting a neutral charge, okay? So meaning that the overall charge on the compound is equal to 0. So in that case, we would write it as Al N. Okay, so then the charges, that 3+ and that 3- balance each other out to add up to a total of 0, a neutral charge. Does that make sense?
Mhm.
Dr. Henry, so you said that aluminum's trying to be like nitrogen?
No, I said aluminum.
Like neon? Oh, okay.
Okay, so remember the noble gases, that's who they're wanting to be like. But
Mhm.
aluminum gives up its electrons in this case tonight.
Oh,
Okay.
okay.
Does that make sense?
Yeah.
Okay, good. Now let's see how much it makes sense because I'm going to start throwing stuff at you.
1, 2, 3.
Okay, so if I have potassium and phosphorus.
Potassium would be +1.
Be -1, right?
Negative.
No, go with your
It'd be a
first guess.
positive.
It
It'll
would
be positive. Yes, because here's potassium, right? Now, if it loses an electron, what happens?
It becomes positive.
It
Oh,
becomes positive,
yeah.
right? Because electrons are negatively charged. Okay, and then what about phosphorus?
It'll be -3
Okay, so phosphorus is going to be -3.
or 3 negative, the way you actually write it.
That's right. Okay, so how many potassiums will I need to balance out that -3 for phosphorus?
1.
So you're telling me 1 + 1 - 3 = 0?
It's gonna be 2, right?
So you're saying 2 - 3 = 0.
3.
3.
You're gonna
Sorry.
need 3. Okay, I'm glad you guys are working on that math there, right? So we'll need 3 of those guys, okay? 1, 2, 3, right? To balance out that -3. So that's 3 - 3, that equals 0, okay? So then when we write it together, when they come together, because positives and negatives, what happens? They attract. They're going to come together, but it's going to take 3 of them to balance out phosphorus.
Okay, that makes kind of sense now.
Okay. Makes sense?
Yeah,
Okay.
it's coming together.
So what
That's
is
good.
this called again? Just balancing them out?
What was that?
What is this called again? Like if it were to be on the exam, how would it be in a question?
It would be like, so what would be it would be the ionic compound. What ionic compound would form between potassium and phosphorus, or ionic bond? Because this is ionic bonding, because they're forming ions and the ions are attracting to each other. So that's the ionic bond. Okay.
Thank you.
Okay, so let's make it a little bit challenging, more challenging.
Just a little
Okay.
bit.
So let's see if we had, let's do. C and Mg.
1, 2, 3, 4. Carbon.
Magnesium would be 2 positive.
Okay.
Carbon would be 4 negative.
Okay. So. how
So
can I
for like
balance it?
this one, why would you choose negative or positive for carbon?
Because magnesium is going to be giving up electrons.
Mm-hmm.
And then so there are going to be these electrons sitting there. And carbon is like, these free electrons, what can I do with them? Is it going to want to get rid of them? You know, and just throw a whole bunch of electrons away? He's like, this is easier for me just to take. Right? So in this case,
Okay.
carbon is going to be like, hey, all mine.
Okay.
Where do you get the 2 from? The 2 positive?
Because it's losing 2 to be like neon.
Because it wants to be like neon. Here's magnesium, right? 1, 2, and then it's just like neon. Remember, your goal is to try to be like a noble gas, either by giving or taking, or by sharing, which we'll talk about sharing here in a minute.
Hey, Dr. Henry, how come magnesium wouldn't be like argon?
You
Too
tell
far.
me. Think about it. If you have to walk,
It's the same, they're in the same row.
But
okay,
it's
wait,
further.
listen to this, Diane. If you have to walk 2 blocks
I
to
can't
get
hear
to
you.
the store, if you have to walk 2 blocks to get to the store, or if you have to walk 6 blocks to get to the store, which one would you do?
4, 5, walk 2.
You would walk 2, right? So it's easier for it to lose 2 electrons.
Oh,
Now, always, you want to think about it in ease. Right here. Here's magnesium. 1, 2, right? Neon is right here. Where if you're here, you have to go 1, 2, 3, 4, 5, 6. That's a lot more energy.
yeah, you're right.
So you want to be lazy.
And we already are.
Yeah. Okay, so we're stuck here, right? So we're at the point where we have magnesium 2+, and we have C 4-. So how many magnesiums will I need to balance out? How many magnesium ions will I need to balance out that carbon ion?
2.
Magnesium 2, C.
2, so it can be 0.
So I'll need 2 of these guys, right? So I like writing them out because it makes it easier for me to see. So then it'll be C, oops, Mg2, C. You guys get that? And you notice, now pay attention, pay really close attention. You notice there's no charge on it, right? So the goal is to make sure that it doesn't have a charge. Charges are balancing each other out, okay? And so you don't want to write it with a charge. Does that make sense?
Mm-hmm.
Okay, so the second thing that you'll notice is that the positive ion is going first. So we always put the positive first, and then we put the negative. Okay, so magnesium went first, and then carbon. Okay, so that's the way that you would always do it. That's Daisy, are you ready? That is an IUPAC way of writing an ionic compound. Positive comes first, negative.
So Dr. Henry, so
Yep.
we're only getting the positive one to balance out to 0.
Mm-hmm.
We're not worried about the negative one.
No, they're both balancing out, right? You're worried about the
They're
negative.
balancing together.
Yeah.
Oh, okay.
Does that make sense? Because you don't see a charge on either of them, right?
Right.
Yeah.
Okay, yeah, that makes
Yeah.
more sense.
So, but they only do that when they come together. When they're by themselves, they have that charge. They have their own little charge. Okay, so they can be by themselves under special circumstances, but when they come together, they form a compound, an ionic bond, okay, where they balance each other out. Okay, so you want to try one more? And then we can try moving on?
Yes.
Yes, please.
Okay, so let's give one really hard now. So let's do palladium. Now, remember when we talk about the guys down here, we're just going to count the P's and the S's, okay? So anything below here, we're just going to be looking at the P's and the S's about the valence electron, okay? So we'll do, actually, I'll give you an easier. The aluminum. And neighbors.
Aluminum would be 3 positive
The aluminum would be 3 positive.
and 4 negative.
That's right. Oops. Okay. So what is it going to be our compound?
Al4Si3.
Al4Si3. That is correct. Good job. So we'll need 4 of these guys. And 3 of these guys. They both will add up to 12, right? Four minus 4 minus 4. So that's minus 12. And then this is 3 minus 3 minus 3 minus 3. So that's positive 12. So 12 minus 12. Piece of cake. Good, bad, or ugly?
Good.
Okay. Okay, so that's an ionic compound. Okay, so let me tell you a little bit more about ionic compounds. Okay, so ionic compounds are basically held together by ionic bonds. Ionic bonds is just that positive and that negative coming together to balance each other out. So there's positive and negative forces that are charged up. So normally at room temperature and at normal pressure, ionic compounds are going to be solid most of the time. Not 100% of the time, but most of the time, okay? And these solids are basically going to have, they're going to form what we call a crystal lattice. And so what a crystal lattice is that you're basically going to have a positive charge, a negative charge, positive charge, negative charge, positive charge, negative charge. And so they're going to be alternating top and bottom, up and down, positive and negative, and then left to right, positive and negative. And that's going to be how they're interacting. So you have an atom that's completely positive. So it's going to surround itself by things that are negative. And then that negative is going to surround itself by something that's positive. So you're going to get nice defined structures as a result of that, called the crystal lattice. And I'll show you a picture down here. Now, ionic compounds, they're always going to end up being neutrally charged. So your goal is to be neutrally charged if you're an ionic compound. So your positives have to balance out your negatives. Okay? That's what we all want in our relationships. Right? We want them, you know, your other half needs to balance you out, right? So you guys are a nice neutral charge. Right, Daisy? She's making the face.
No, right, I'm just moving.
Okay. So, and then the other thing is that the because these guys are, it's a strong bond. This ionic charge is a very strong bond that keeps it together. So it takes a lot of energy to sit there and separate from each other, or it takes water. Sounds weird, huh? Right? So you can just add water, and a lot of times you can just separate the two. But you can't separate them unless you put a lot of energy in, or you put water in. Okay, and we'll talk about that a little bit later, why that's the case. So you guys, you look at salt, right? Have you guys played with salt before?
Mhm.
Sodium chloride. Okay, so salt is a very, very good example. So if you put salt on the stove, can you melt it?
No.
Will it become a liquid?
No.
No, because we're not putting in enough energy in. If we put enough energy in, we could actually, and when it melts, it actually separates that positive and that negative, right? And so, but it takes a lot of energy. Our stoves can never get up that high, okay? So, but if we put it in water, doesn't it dissolve? And that actually separates it into its ionic forms. It has that plus and that negative in solution, and they're separated from each other. Okay, so that's an example. So it's really, really strong unless you put water in it. Then water just says, it gets underwater and it, you know, loses its mind. Okay, I'll talk about that a little bit later. Okay, so here's an example again, sodium chloride, right? So sodium metal is very, very volatile. The metal by itself, it is very, very reactive. Chlorine gas is very reactive. When you put them together, it makes this huge reaction, right? And then you get salt. Okay. And salt, how many of you guys eat salt? Okay, so how many of you guys have blown up because you ate salt? Not got bloated, but blown up, like physically exploded.
No.
No, huh? But it's made up of sodium and chlorine, right? Both things that are, if you put in your mouth, would blow your mouth away or kill you, one or the other. Right? Chlorine gas will actually, it'll actually start reacting with your skin and your bones and all that stuff, and just basically rip them apart, kind of blow it up. Sodium metal would actually explode in your mouth because the liquid and stuff and the air just, it's very, very reactive, right? But it doesn't happen when we eat sodium chloride. Why not?
Do they change the formula, or like do they
Neutralize it?
Oh, wait, somebody said it. They neutralize each other, right? Because we have sodium chloride, which is an ion, right? So they've already exchanged. So the reason why this reaction is so volatile, so violent, is because sodium is so anxious. Sodium metal is so anxious to lose an electron that it's like, oh God, I get to lose an electron. And then chlorine is so anxious to gain an electron. It's like, oh my God, I get to gain an electron. It's violent. They're just like, bam, you know, it's like really wild, crazy, violent interaction, right? Reaction, okay? Because they're exchanging that electron. But here we have sodium, which is already positive, and chlorine, which is already negative. They're already stable. They're just coming together, right? Based upon charge. And so we can eat salt without any problem, but we can't eat sodium alone. Does that make sense?
Mm-hmm.
Okay. So that's that concept. Remember, being like the noble gases. Well, these guys are already like the noble gases, right? And then because they're positive and negative, they get a chance to interact. And so they also neutralize each other. And so because they neutralize each other, we're able to sit there and digest it and eat it without our mouth being blown up. Okay, does that make sense?
Yes.
So that's why it's important to read labels, right? So you don't want to sit there and put sodium metal on your pasta, you know? Okay, so this is just basically showing you what goes on, right? So here we have sodium, the sodium atom, it loses an electron. And then the chlorine atom gains that electron, okay? And then now the sodium ion is formed and your chlorine ion is formed, and then they come together to form salt. Now this is just showing you that crystal lattice, right? So you can see this here is the sodium, this is the chlorine. So sodium, chlorine, sodium, chlorine, sodium, chlorine. You see how it's alternating based on charge? These are just 3 different models of showing you exactly the same thing. And then key thing here is that it's surrounded by those, right? Chlorine atom surrounded by them, where we have here we have the sodium surrounded by the chlorine, right? So they literally surrounding those charges and stuff, but in an organized manner. So because you have these positive and negative charges flowing everywhere, they also are allowed to conduct electricity. So when we put sodium chloride in water, we can use that to sit there and conduct electricity. Or we can just try to melt it with a lot of heat and make it a liquid, and it'll also conduct electricity because you have those free ions to be able to conduct electricity for us. Make sense? Okay, good. Okay, so that deals with that give and take. So that's our ionic, right? Ionic, giving and taking. Okay, so let's talk more about that covalent. So we talked about the 2 forms of covalent, right? We talked about polar and nonpolar. Okay, so I'm going to give you an example of nonpolar first because it's easy, and then we'll talk a little bit about polar. Okay. Okay, so we know that covalent bonding is sharing electrons, right? So when 2 or more atoms share pairs of electrons, right? So these bonds are permanent and they're not going to be broken until we make chemical changes. So they're basically going to be overlapping of electron densities. So they're literally sharing. So it's kind of like your arm, sharing an arm with somebody. You literally tie your arm with them and don't let go, you know, or fraternal twins, you know, or what are the twins that are attached to each other? I can't think of it right now.
Conjoined.
Conjoined? Yes. So we could have conjoined twins, right? So they're physically attached to each other. That's kind of like what's happening here. Okay. So the way it works is, again, they're sharing electrons. In the case of, we know that hydrogen is diatomic, right? It exists as a diatomic element. That basically means that the hydrogen is sharing a bond with the other hydrogen. So they're sharing that 1 electron so they can be like the noble gas that is closest to them, which is helium, which has 2 electrons. Okay, so I'm going to say this right now. I'll say it again in a few minutes. But hydrogen will never, ever, 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 ever have more than 1 bond. Okay? Hydrogen will never, ever, ever, ever have more than 1 bond. Hydrogen will never, ever be a center atom because it can only have how many bonds?
1.
No.
Okay? So we should never, ever put hydrogen in the center. Well, somebody was adamant about it. They put the peak. Okay.
Almost burning.
Okay. So how are you guys doing so far right now? You guys pretty good? Okay. So the way that we sit there and we determine bonding, we have to use Lewis dot structure, right? So we said, in this case, we had each of these guys had 1 valence electron, right? Each hydrogen has 1 valence electron. So we want it so it's like helium and it has 2 electrons around it. So we put these guys together. A line represents the sharing of 2 electrons. Okay. So, and we count the number of electrons around this hydrogen, that's 2. We count the number of electrons around this hydrogen, it has 2. So it reaches what we call its octet. Hydrogen only needs 2 around it, so it reaches its octet. Normally octet means 8. So after this, we're going to be talking about reaching that 8. Okay, we have oxygen. How many valence electrons does oxygen have?
6.
Oxygen has 6 valence electrons. Okay, so in this case, we need to find a way of bringing these guys together because we know that oxygen is also that high, so that each oxygen has 8 electrons around it. You told me oxygen has 6 valence electrons, 2 times 6, 12. So we have 12 electrons to work. So we're going to bring these guys a little closer together. Okay, we need to share some electrons, obviously, so that everybody can have 8 around them. How many electrons are we going to share so that each oxygen has 8 electrons surrounding it?
4.
4. Okay, so I'm going to move 2 in the middle. That's right, it's going to form a double bond. Well, that's if it lets me move it. So there's 2 right there. Okay. Okay, so it's going to be sharing. So rewrite this. Anytime that we have 2 electrons being shared, we can draw a line, and it looks so much prettier than having all those dots everywhere. Okay, so how many electrons were we working with?
12.
We're working with 12. So that's 2, that's 4, that's 6, that's 8, that's 10, that's 12. So that's 12 electrons. Okay,
You have to make sure that there's 8 around.
that's right. So that's 2, that's 4, that's 6, that's 8 around this oxygen. 2, that's 4, that's 8 around this oxygen. Piece of cake?
Yeah.
Okay, what about nitrogen?
Nitrogen has 5.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's a total of 10. We have 10 electrons to work with. So how can I set it up so this guy reaches his octet with those 10 electrons, with where nitrogen and nitrogen coming together?
Triple bond.
Just bond.
One's right there.
Okay, triple bond. And lone pairs.
Yeah.
So these electrons that aren't involved in bonding, they're called lone pairs. I think I said that the last time, but just to remind you. So if we count, that's 2, 4, 6, 8, 10 electrons. So we have 8 around this one, 2, 4, 6, 8, and we have 8 around this one, 2, 4, 6. Piece of cake?
Yes.
Okay, so let's make it a little more challenging. So what if we have CO, carbon monoxide?
Seven. Oh, I mean,
You have 10.
10.
So we have 10 to work with. An electron. Carbon has 4,
4.
and oxygen.
6.
Okay, so what do we need to do?
That one is C. This one. 1, 2, 3, 4. 2, 4, 6, 8, 10. 10.
Would it be a double bond?
Okay, so we did a double bond. That means we're taking 2 of these guys, get them in here.
7, 8.
So does that work out?
No, you need a triple bond.
I need a triple bond, that is correct. Two, 4, 6, 8, 10, and then 2, 4, 6, 8 around carbon, 2, 4, 6, 8 around the oxygen.
Mhm.
Okay. Good, bad, ugly.
And give us one more.
One more? Okay,
Yeah.
let's see. All the ones I want to give you are big ones, but okay, let me think. Let's do.
Give us one that's going to be on the test.
Actually, I'll do this one.
These are the ones.
Okay, here we go. So,
There's 1, 2, 3, 4, 5.
So we have 8 electrons to work with.
we have 8 electrons to work with.
So nitrogen has 5.
Okay, nitrogen has 5.
And you need 3 of the hydrogens.
Hydrogen.
Okay, so I need 3 hydrogens.
Mm,
Okay, so who's going to be in the middle?
Nitrogen.
3, 4, 5.
So again, it doesn't matter where we put them, right?
Not
Or
initially,
does-
but eventually it will matter. Yes, but it's going to matter in this case, right? Because how many bonds are we going to have?
Well, we need to follow the octet rule. So then,
3 bonds.
We're going to have 3 bonds.
Mm,
I heard somebody say that. So we have between each hydrogen and nitrogen. And then we're left with the lone pair. So does that obey the octet rule?
2, 4, 6, 8. Yes, because N has 8 around and hydrogen can technically just have 1.
You may have 2 electrons.
So yeah, 2, 2, 2. Because it's sharing 1.
That's right. Okay,
mm.
simple.
Yes, these are.
Okay, so let's make it a little more challenging.
No.
Should have never said simple.
Okay, so let's talk about when we have a center atom, right? So we determine who goes in the middle based upon strength. Okay, so the guy who has the strongest electronegativity isn't going to want to go in the middle, right? It's kind of like the bigger brother. I mean, you guys all have siblings, right?
Mhm.
Yes.
How did you guys decide who goes in the middle when you guys went on road trips?
Forward center.
The
smallest
smallest
one?
or the weakest, right? That's the way we decided because my little sister, when she was little, I used to just push her in the middle, right? I'm like, you can't sit there. She's like, no, I'm sitting next to the window. I said, nope, push her in the middle, right? That's all, always, right? So the one who has the weakest electronegativity gets pushed in the middle, okay? Now here's something else you always want to keep in mind. Carbon likes to be in the middle. Carbon's a little bit of a whore, okay? So carbon likes to have 4 bonds if it can have 4 bonds. It can take up to 4 bonds. It's happy to do it. It's like, hey, put me in the middle, right? So carbon enjoys to be in the middle. So if you have a compound that has carbon in it, 99% of the time it's going to be in the middle. 99.999% of the time. Okay, so who's going to be in the middle?
Carbon.
Carbon.
Carbon. I still didn't show you guys that video. Remind me after this, I'll show you the video. Okay, so carbon has how many valence electrons?
Carbon has 4.
Okay, oxygen has how many?
And you have 2 of them. Just 12.
Okay, so altogether we have how many electrons to work with?
16.
Okay. Okay, so what do I need to do to make this
So
work?
you're going to do a bond between the carbon and the oxygens on both sides.
Okay. So does that work?
Wouldn't it be a double bond?
Ah, double bond.
The carbon can have 8 around.
That's right. You need to have 8 around it. Okay, is it both double bond on both sides?
Mm-hmm.
Yes. And then 4 lone pairs.
Okay. So 2, 4, 6, 8, 10, 12, 14, 16. That's the right number. We have 8 around this oxygen. We have 8 around carbon. We have 8 around this oxygen. Piece of cake?
Yeah, Dr. Henry, can you also do it another way, or that's the only way you can do it? Because I did it like that. I mean, right now when we're doing it, I did it. So I had the carbon in the middle, and then I had a one single bond, and then I put 2, 4, 6 on the oxygen.
So technically, okay, so yes, technically you can do it this way. where you
But
have
then I
6
did it
bonds.
how you guys did it, but I the first time I did it was like that.
Yeah, so technically this would work, right? So that's 2, 4, 6, 8, 10, 12, 14, 16.
Mhm.
Yes, this would technically work, but it's not the best way. And I'll explain that to you here in a second. Okay. Since you're forcing my hand. You guys are all pushing me like ahead of the schedule here, right?
Sorry.
Well, this is the most ideal way because it's more stable. So this guy can exist, but it's less stable. It doesn't exist at all. Okay. So, and the way that we can determine that is by calculating the formal charge. Okay, so I'll explain that to you right now. Force my hand. Is that
Sorry.
Diana?
Yeah.
Good job, Diana. So you guys are keeping me ahead of the game. So on your homework, you guys have something called formal charges. Now I'm going to show you how to calculate your formal charge. And then I'll show you the formal charge. And I have to remind myself to show the other class. I keep forgetting.
I was gonna say I logged in last week and I don't remember a video.
Yeah, because you weren't there to remind, or you were there, but you didn't talk about it. Oh, you didn't remind me of
I
it.
felt awkward because it wasn't really like my week.
Okay, so to calculate the formal charges, we want the valence electron on that atom, the number of valence electrons. I can spell minus the number of lone pair electrons. That means all of the electrons that are not bonding. And then we want the number of bonds.
Minus the number of bonds.
Minus the number of bonds. Yep. Okay. Okay, so we want the formal charge to be as close to 0 as we can possibly get it, right? Ideally, we want it to be 0 for each of the different atoms. Okay, so if this one up here, we'll start up with the one up top here. I'll circle it. Maybe. We're going to start off with this one. Say it in pink. Doesn't listen. Okay, there we go. We're going to start at the one in pink. Okay, so we'll start with this first oxygen. So how many valence electrons does oxygen have?
4.
How many valence electrons? 6. Okay, minus the number of lone pair electrons.
4.
Minus the number of bonds.
2.
Okay, we add that up, that should equal 0. Okay, now for the carbon. How many lone pair electrons does it have?
4.
4.
How many, I'm sorry, how many valence electrons does it
4.
have? Now, how many lone pairs electrons does it have?
Lone pair 0.
0, okay. And then how many bonds?
4.
4.
Okay, and the other oxygen is going to be exactly the same, so it's also going to be 0. 6 minus
Is that the
4.
goal, to get 0 every time?
That's right, your goal, and that shows stability, right? So usually, if you have this guy, it's going to be the most stable form. Sometimes you can't get away from having a charge, but you want to try to get it as close to 0 as possible. Okay. Now let's do this.
Because that means we made it stable.
That's right. That means that we made a stable molecule. Yep.
Okay.
Okay, so let's do this one right here for wood. Do that one in orange. If it listens to me. Orange. Okay. Good. Okay, so that first oxygen. How many valence electrons?
6.
How many lone pair electrons? This first oxygen.
Oh.
4. I mean, 1,
6.
2, 3, 6.
Doing this one now. 6. Okay. And how many bonds?
1.
1.
Okay. We add that together, we get a -1. Okay, carbon,
Carbon has 4,
4 valence electrons. How many lone pair?
0,
And how many bonds?
4.
Okay, and then the oxygen, the other oxygen, valence electrons,
So it has
Six.
6,
lone pair,
2,
and bonds.
3.
3.
So that should be a +1. Okay, so which one is better? The pink or the orange?
The pink.
Oh, okay, okay.
That makes sense.
So that's the reason why that one is a better choice. Okay, so again, those are called formal charges. Everybody got that down? And you have a couple of questions, a few questions on your homework.
Thank you.